Okay, so previously we used this plane of rotation. So let's remember a few facts. First is the point that for gate the angles are with respect to the uh, axial plane, axial plane, and not the plane of rotation, plane of rotation, or the otherwise also called as the uh, tangential plane. So this is a very crucial distinction. Now we were to actually again draw this diagram. Now what is the objective of this? So objective of this whole thing is that we need to graphically prove that the blade angle is equal to the relative inlet relative air inlet angle at I is equal to 0, that is incidence. Okay, so the same diagram, we rotated the plane, the orientation was rotated here, as you can see. So let's draw the diagram again so as we can get a clarity on what is happening. uh, so let me do one thing. I can draw the plane and copy this. So this will be copied so that I don't mess up again. Okay, paste. So what we can do, right, this is here. Now let's draw that diagram again because we need to graphically prove it. Okay, and the rotation of the, so this is the horizontal plane and this is the axial plane and this is the tangential plane or the plane of rotation. So this is axial plane and this is the plane of rotation. By plane of rotation we mean the plane along which the blades are moving. Okay, so according to the diagram, this should be the, wait, uh, according to the diagram, this should be made the, uh, this is the cross section of the blade. So the relative air that is coming, that is approximately like this. Okay, so this is the zero incidence condition where the relative wind is directly hitting the chord line of the blade. So let's denote the chord line with another color so that we may able to identify it. So this is the chord line. Okay. So the angle subtended by the chord line with the axial plane is also the blade angle in our case. But the actual definition is the angle subtended by the chord line with the plane of rotation. But in this case, we are taking this as beta blade at inlet. Okay. Then this is the relative wind. Now we know that the flow, or sorry, not the flow, the blades are moving in the tangential direction or the plane of rotation with u. So this is the blade velocity. So the angle or the direction of the absolute velocity will be this v1. So this is the triangle. Now we know that the air inlet angle is the angle that is subtended by the relative air, that is the V1 part with respect to the axial plane. So if we draw an angle, wait. So if this is like this, okay, if this is like this is W1. So this should be the beta. So yes, this this is the horizontal. This would be beta 1 as from this figure here. Okay, and then this is beta 1, and therefore by geometry this should also be beta 1. So by geometry, since the chord line and the axial plane, so for zero incidence, beta 1 is equal to blade angle is equal to beta 1. So this is proved from here. So it is all about from axial plane. Now, assuming that the relative wind is not hitting at the leading edge of the blade at in zero instance, but some other incidence. So assuming that the blade now, sorry, okay, let's use another color. Mm, Okay, let's use green. Assuming that the relative wind now is hitting at some another angle, this is the relative wind that is hitting the blade. This is the U. So the angle subtend, and this is the direction of the V1 now. So the angle subtended will be beta, and this is beta. So in normal, beta is equal to this is theta, and this is also theta. Wait. So this will be okay. So beta one. So this whole total will be wait. This is beta one. This is beta beta B1 minus wait. If this is beta, this is beta, and this is beta B1. So okay, that is the condition. This is for the inlet angle. Okay, at exit, we have to now check. Okay, this is for this one. అంతే కదా? Now the relative velocity which is entering the stator, which the stator will be seeing in the same direction as C2. But in this case, C2 will be the angle, no, this is beta. Now the angle between the velocity component and the axial plane will be the alpha 1, which will be the angle which we are calling as uh, exit or angle of deviation. deviation. That is the angle that the absolute vector is corresponding to its original path, which is V1. And the beta 1 is the blade angle, that is the angle the blade is with respect to the air at zero angle of incidence. So this is it. Okay. So one small correction and like very good conceptual understanding. So the angle that is subtended by the absolute velocity vector of the inlet and the axial plane, this is called the angle of absolute absolute flow angle. Okay, so by convention, beta would be the relative flow angle or angle of the relative flow. Now, keeping that in mind, all right. So let's do one thing. Let's again redraw the diagram, but in a different condition case. Mm, let me use this one. Maybe this one. Yes. So assuming there is another wait. Not this one. Okay, this should be fine. So assuming now the flow is that is being seen by the blade is this is W1. So the relative absolute the absolute will be this one V1. The angle now subtended, and as we know the angle subtended by this with the axial plane is beta. That is the angle of the relative airflow. Okay, so this will also be beta by geometry. Now, since we know that the angle formed by the chord line of the blade to the axial plane is the blade angle. So, when if we extend this to find out the angle of incidence, so this the angle between the chord line and the relative flow is the angle of incidence. So, so okay, let's proceed to the next part. Maybe let's see. So we have done till here. Now, now there is a confusion among students. There are two types of notations for blade angle. So one notation is for the flight pilots and the propeller terminology. Now, according to this, the blade angle is blade angle is the angle between the plane of rotation to the uh, chord line of the blade cross section. Now there is an another terminology where we are using the same. Now, another problem here that is coming to us is that the angle of attack here, AOA, angle of attack, is the uh, angle between the chord line of blade and airflow. But in case of the turbo machinery, the whole thing changes. Wait a minute, let me do something. Let me just actually we are going to proceed for this as well to check the exit conditions of a rotor in an axial compressor. Now why I am making this is because I have been facing the same issue. So if anyone else is also facing the same issue with the confusing terminology, this would act as a baseline for them to be able to not get confused in the turbo machinery part and understand the topic more on an intuitive basis. So this is the first. The second is what we study in turbo machinery. So here generally we the reference here the reference plane is the plane of rotation, but here the reference plane is the axial plane. And another thing that is mentioned here, or we can say is says here, is the definition of blade angle. Here, in case of turbo machinery, we define the blade angle as the angle between the chord line of the cross section of of blade to the axial plane. So due to this, the main problem here is both are referred to as blade angles, but here in case of propeller terminology, this is also called as the pitch of the propeller. So blade angle of the propeller or pitch of the propeller means the same. So this is the general terminology confusion that we face. Now the second part where there is a change in terminology when it comes to the turbo machinery conditions is the part of angle of attack. Now the very same AOA in case of propeller which we use is nothing but the angle of incidence in case of the turbo machinery, which is nothing but flow minus blade angle. So although these are the same topics of the same uh, flight mechanics, but the terminology that we are using is totally different. So this is the point where the confusion occurs most of the time. Now, second is how do we calculate the velocity triangle intuitively in case of a axial compressor. So my basis of understanding is when the relative flow of the air enters the compressor rotor. So it first encounters the curved nature of the blade cross section. So the area of the channel or the streamline starts to expand as the flow carries forward. So assuming a subsonic inlet into the compressor, and this is the area, we can come to this conclusion using the uh, continuity equation for steady flow, assuming everything is steady flow, and non viscous. And here we are also assuming another thing. This is an irrotational flow at the inlet because rotational flow will induce a swirl component, which is also called as a pre-swirl in case of an inlet. So, since the relative velocity of the air decreases as it passes through the rotor, we can draw a diagram here so that we can accurately estimate what is the issue and clarify it. So, this is the axial plane, and this is the plane of rotation. Because why I'm using this convention is because this is the same convention which is used in gate exam. So that is why we are using this convention. Now we know that from the inlet condition, we know how it behaves. So assuming here, so this is the inlet W1 relative at inlet, and wait, so just a minute. Now, why I am drawing such a big diagram? Because it will be easy for understanding where the issue is. So this is W1, and so this is the inlet diagram. Assuming this is the U, so this becomes V1. Now we know from convention that the angle subtending from the axial plane of the relative velocity is known as the beta 1. This is beta 1, and this is alpha 1. Okay. Now let's take the case of the exit plane. Now, as we know, if we see from this diagram, if we understand it intuitively, as this goes, the W2 is less than W1. So under vector notation, we have to first understand that W2 is less than W1. The U remains constant across the whole section or the stage. Now, one thing we need to understand is that the flow is coming in this direction. So, when a tangential component hits it, the orientation of the flow changes like this. So, as you can see, it is pushing. So, this is the action which is happening. So, if we notate this, initially it was in this condition. Now, this will move like this. But since the V2 W2 is shorter than W1, the length of the vector will be smaller than the W1. So here we draw another diagram denoting the this is the W2. This is for the exit. Now we since U is constant, we can safely connect it with the starting line, and here then we will be able to get the V2. Now from observation we can say that it is, I mean, people can get confused that V2 should be less than V1, because since U is constant and W2 is less than W1, it is a misnomeric understanding that V2 will be less than V1. But one thing we need to be very careful about here in this condition is that if you observe that the tangential component of the U, that is the blade velocity, has added a swirl component to the uh, relative velocity. So the W2 will be greater than V1 because of the additional swirl component of, of relative velocity, which has increased it. So that is the reason of it. So, so this is the diagram that I had drawn right now. If I take a copy of it so that on the next page I can make it even neat. So this is the diagram. Okay. So this is the diagram of a compressor. This is the velocity triangle diagram for a compressor, axial compressor rotor. So this is the inlet condition, inlet, and this is the exit condition from the rotor blade. So that's it.